October 2025, a month that astronomy enthusiasts will mark in their calendars for years to come. Not because of an eclipse, not because of a meteor shower, but because of something far rarer. Two comets, two ancient travelers from the edge of our solar system, both visible in our skies within the same lunar cycle, both carrying secrets from the dawn of planetary formation, and both arriving at a moment when humanity's instruments are perfectly positioned to witness them. This is the story of C2025A, 4 Lemmon, and C2025R, 2 SWAN, two messengers from the Oort cloud, that vast spherical shell of frozen debris surrounding our solar system like a cosmic snow globe. Objects that haven't felt the warmth of our sun in over 10,000 years. And now they're here, racing inward, heating up, transforming before our eyes. Comment below, have you ever seen a comet with your own eyes? Let's rewind to where this story begins. January 9th, 2025, the deserts of Arizona. Mount Lemmon Observatory sits at an elevation of 2,791 meters, where the air is thin and the stars burn brilliant against the black. Here, robotic telescopes scan the heavens every clear night, part of the Mount Lemmon survey. Their mission isn't beauty, it's protection. They hunt for asteroids that might threaten Earth, cataloging near-Earth objects that could someday pose a danger. But on this particular night, the automated system flags something unusual. A faint smudge of light moving across the constellation Cetus, too diffuse to be an asteroid, too fast to be a distant galaxy. The coordinates are transmitted automatically to the Minor Planet Center in Massachusetts, the organization that serves as the official record keeper for everything orbiting in our solar system. Within hours, other observatories confirm it. Follow-up observations from Chile, from Spain, from Hawaii. Each telescope adds precision. Each measurement narrows the uncertainty. And the verdict becomes clear. This is no asteroid. This is a comet, a long-period comet with an orbital period calculated at roughly 15,000 years. The last time this object passed through the inner solar system, humans were painting caves and hunting mammoths. It receives its official designation, C2025A, 4 Lemmon, named after the observatory that discovered it. The astronomical community takes notice, but there's no alarm. Long-period comets appear every few years. They're fascinating, certainly, scientifically valuable, absolutely, but not unprecedented. Scientists begin calculating its trajectory, predicting when it will reach perihelion, its closest approach to the sun, when solar radiation will vaporize its frozen surface and create the spectacular tail that makes comets so distinctive. And then September arrives. Far above Earth's atmosphere, a spacecraft circles in the darkness, SOHO, the Solar and Heliospheric Observatory. A joint mission between NASA and the European Space Agency, launched back in 1995, still functioning flawlessly 3 decades later. Its purpose is studying the sun, monitoring solar winds, tracking coronal mass ejections, understanding the star that gives us life. But SOHO carries another instrument, SWAN, the Solar Wind Anisotropies Detector. And in September 2025, while scanning hydrogen emissions in the solar wind, SWAN's automated systems detect something unexpected, another diffuse object, another comet, this one approaching from a different angle entirely, coming in from the southern celestial hemisphere. The discovery catches astronomers by surprise. Finding one bright comet is fortunate. Finding two in the same year approaching peak visibility in the same month, that's extraordinary. The Minor Planet Center processes the data, confirms the orbit, and assigns the designation C2025 R2 SWAN. Suddenly, October 2025 transforms from interesting to historic. Observatories around the world begin coordinating observation schedules. Research teams apply for telescope time. Astrophotographers plan expeditions to dark sky sites, because what's about to happen is something that occurs statistically once every 10 to 15 years. two active comets visible simultaneously from Earth. Subscribe now, because what these comets reveal will change how we understand the origins of our solar system. By late October, both comets have moved into optimal viewing positions, though from different perspectives. Understanding where they are requires understanding orbital mechanics, the invisible architecture of gravitational forces that governs every object in space. See 2025. A 4 Lemmon has crossed the orbit of Mars and continues inward. As of October 27th, it sits approximately 0.4 astronomical units from Earth. That's roughly 60 million kilometers, about 40% of the distance between Earth and the Sunday. For Northern Hemisphere observers, it rises in the eastern sky before dawn, a pale green smudge visible through binoculars, hovering above the horizon like a cosmic lighthouse. See 2025 R2 SWAN follows a different path. Its trajectory brings it closer to the Sun, approaching perihelion at just 0.9 astronomical units. It's best visible from southern latitudes, appearing in the constellation Lupus in the pre-dawn darkness. Southern Hemisphere observers report that it's brightening rapidly as solar heating intensifies. NASA's NEOWISE satellite, designed to scan the sky in infrared wavelengths, tracks both objects continuously. Ground-based observatories like Gemini South in Chile and the Cerro Tololo Inter-American Observatory coordinate their observations, building detailed maps of both comets' trajectories. Every night adds precision. Every measurement refines the orbital calculations. And here's what makes this moment so scientifically valuable. Both comets are experiencing nearly identical solar conditions at nearly the same time. They're both receiving similar levels of solar radiation. Both are heating at comparable rates. This creates a natural experiment, allowing astronomers to compare how different cometary compositions respond to the same environmental conditions. Comets aren't just pretty, they're archives. Time capsules containing materials that haven't changed significantly since the solar system's formation 4.6 billion years ago. When our sun ignited and the protoplanetary disk began cooling, volatile compounds condensed into ice crystals far from the newborn star's heat. Water, methane, ammonia, carbon dioxide, complex organic molecules. These ices accumulated into larger bodies, eventually forming the Oort cloud, a vast reservoir containing billions of cometary nuclei orbiting in the darkness beyond Neptune's realm. And now, two of those ancient relics have fallen inward, drawn by gravitational perturbations, beginning their long plunge toward the Sunday. As they approach, solar radiation begins sublimating their surfaces. Frozen volatiles transition directly from solid to gas, bypassing the liquid phase entirely, creating the distinctive fuzzy appearance called a coma. But here's where it gets fascinating. The two comets display different colors, different chemical signatures, different personalities. See 2025, a 4 Lemmon glows with a greenish tint. Spectroscopic analysis reveals why. Its coma contains significant amounts of cyanogen and diatomic carbon. These molecules absorb solar ultraviolet light and re-emit it in the green portion of the visible spectrum. It's a color we've seen before in other comets, but the intensity suggests Lemmon formed in a region of the early solar system particularly rich in carbon compounds. See 2025 R2 SWAN shows a bluish hue. Its spectrum is dominated by hydroxyl radicals and hydrogen emissions. These come from water molecules being broken apart by solar radiation. The process is called photodissociation. Sunlight strikes a water molecule with enough energy to shatter it into hydrogen and hydroxyl fragments. These fragments fluoresce, creating that characteristic blue glow. The James Webb Space Telescope, humanity's most powerful infrared observatory, has turned its attention to both comets. Early spectroscopic results reveal even more detail. Lemmon shows elevated methanol levels and unusual carbon dioxide signatures. SWAN appears rich in water ice, possibly containing as much as 80% water by mass. These chemical fingerprints help scientists understand the temperature and density conditions in different regions of the early solar system's outer disk. Dr. Tony Farnham from the University of Maryland, a planetary scientist who has studied comets for decades, captures the scientific excitement perfectly. Dual observations of active Oort cloud comets give us a comparative snapshot of how primitive ices behave under identical solar conditions. Think about what that means. These objects formed in the same era, likely in the same general region of space, from the same primordial materials, but subtle differences in their formation locations, perhaps just a few astronomical units apart in that ancient protoplanetary disk, created different chemical compositions. By studying those differences now, scientists can map the chemical gradients that existed in the early solar system. They can understand how temperature varied with distance from the young sunday. They can model how different ices condensed at different locations. This is forensic astronomy, using present observations to reconstruct ancient conditions. Each spectral line is a clue. Each isotopic ratio is evidence. Together, they help answer one of astronomy's most profound questions. How did our solar system form? How did the materials that eventually became planets, moons, asteroids, and comets organize themselves from that initial cloud of gas and dust? The European Space Agency's SOHO team has confirmed something equally intriguing. Both comets show increasing ultraviolet emissions as they approach the sunday. This indicates active outgassing. Their surfaces aren't static. They're dynamically changing, shedding material, transforming in real time. Long exposure images reveal subtle jets and streamers in their comet, evidence of subsurface activity as solar heat penetrates deeper into their icy nuclei. For those of us without access to research telescopes or space-based observatories, there's still a way to witness this rare event. Both comets have brightened enough to be visible through binoculars or small amateur telescopes from dark locations. For Northern Hemisphere observers, the window for Lemmon is narrow but spectacular. Between October 27th and 31st, look eastward before sunrise. The comet appears low on the horizon, requiring a clear view without obstructions like buildings or trees. Its greenish glow distinguishes it from background stars. Astrophotographers with tracking mounts and long exposure capabilities can capture its developing tail, a faint streak extending away from the sun's direction. Southern Hemisphere observers have a slightly longer window for SWAN. Throughout early November, it remains visible in the pre-dawn sky near Lupus. From locations like Chile, Australia, South Africa, or New Zealand, it appears higher above the horizon, making observation easier. Reports from amateur astronomers describe it as distinctly bluish, noticeably different from Lemmon's green tint. Both comets are producing tails, though neither will rival the spectacular displays of comets like Hale-Bopp or Hyakutake from decades past. These are respectable comets, bright enough to see, scientifically valuable, but not the naked eye spectacles that occur once or twice per century. That's perfectly fine. Not every comet needs to be a showstopper. Sometimes the quieter visitors teach us just as much. This double comet event represents more than just a visual spectacle. It's advancing our understanding of prebiotic chemistry, the complex organic molecules that existed before life emerged. Comets are thought to have delivered significant quantities of water and organic compounds to early Earth through impacts during the planet's formation. By analyzing the chemistry of comets today, we gain insight into what ingredients were available when life first appeared on our world. The isotopic ratios measured in both Lemmon and SWAN will be compared to isotopic signatures found in Earth's oceans and in ancient meteorites. Do they match? If so, it strengthens the hypothesis that cometary impacts contributed to Earth's water inventory. If not, it suggests our water came from different sources, perhaps from asteroids in the inner solar system rather than comets from the outer reaches. NASA's Planetary Defense Coordination Office while primarily focused on potentially hazardous asteroids, uses comet observations like these to refine models of how cometary material behaves. Understanding outgassing patterns, tail formation, and fragmentation risks helps scientists predict how comets might evolve if any future long-period comet were discovered on a collision course with Earth. As October 2025 draws to a close, both comets will begin their journey outward. Lemmon will recede beyond Mars, beyond Jupiter, eventually returning to the cold darkness of the Oort cloud, where it will remain for another 15 millennia. SWAN follows a similar path, curving around the Sun and accelerating back toward interstellar space. Within months, both will fade below the detection threshold of all but the most powerful telescopes, but their legacy remains in databases filled with spectroscopic measurements, in hard drives storing thousands of images, in scientific papers that will analyze this data for years to come, in the memories of everyone who stepped outside on a clear October morning and glimpsed these ancient wanderers against the stars. This is what makes astronomy so profoundly human. We are creatures bound to one small planet, unable to physically reach these distant visitors. Yet through ingenuity, through mathematics, through instruments we've built and launched, we can still touch them. We can analyze their chemistry. We can understand their origins. We can read the story written in their ice and dust. Two comets, two messengers from the dawn of everything, both here in the same month, both visible, both teaching us about where we came from and what materials built the worlds we inhabit. If you have clear skies in these final days of October, look eastward before dawn. Find that faint green glow or that subtle blue shimmer. Know that you're seeing photons that bounced off ice formed before Earth existed, before the moon coalesced, before any planet had solidified from that ancient disk of debris. You're witnessing deep time made visible. 15,000 years compressed into a moment, and that moment is now. Comment below. What questions would you ask these ancient travelers if they could speak? And subscribe, because the cosmos is always sending us messages. We just need to learn how to listen.